Hello, this is Dr. Gallego. So I already explained a little bit about what correlation is, and today I want to talk to you about how we actually go about doing a correlation. So when we do a correlation, we leave behind the jargon or the talk of experimentation. We no longer deal with independent and dependent variables, control and experimental groups, and all of that. So what we do to do a correlation is we get a group of people. Usually it's a pretty large group. So I might get as many as 100 people, hopefully more, but at minimal 100 people. And what I would do is I would take two measures for each of those things. Now I'm gonna pick a goofy example just to show you that when two things are related, it does not mean that one causes the other. So I'm gonna say we're working with the kids and the reading level like we did in Hooked on Phonics, right? And so one of the things I'm going to do is I'm going to take reading level for each kid, and I'm also going to take their shoe size. So what I'm going to do is I'm going to get these actual measures off of people. And what I want to do here is I want to make it easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'm going to have shoe size over here and reading level here. And I'm going to, for each kid, let's say this kid had a 3 shoe size and a 1 reading level. And this kid had a 9 shoe size and a 7 reading level. And this kid had a 5 and a 5. So I'm going to plot each child. So child 1 is got a shoe size of 1 and a shoe size of 3, 1, 2, 3, and a reading level of 1. So here is kid number 1. Kid number 2 has a 9 on shoe size, and then on reading level they have a 7. So this would be 1, 2, 3, 4, 5, 6, 7. So where 7 meets 9, this is where kid number 2 is going to go. And kid number 3 is going to have a 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Where those two meet, here's kid number 3. Okay? Now, rather than sit here and plot 100 scores with you, what I'm about to do is put a bunch of dots on this graph. So I'm going to put dots on here, and each dot is going to represent one of these kids, number 4, 5, 6, 7, all the way down to kid 100. So I'm going to get all these 100 dots on here that represent 100 children that I tested, okay? And you'll see that it starts to be a pattern. So what I'm saying is this kid could be number 17, and this kid could be number 32, and maybe here's kid 100. And what you're seeing is a pattern. You see a pattern that emerges in this direction. And that's what tells us that two things are correlated. Because what happens is that correlation is all about being able to predict. And when I have a pattern, I'm able to predict. So let's look at that prediction. Let's say that you tell me my kid's shoe size is a 1, okay? I'm going to predict that their reading level falls in this range here. But if you tell me my kid's shoe size is a 9, my prediction for your kid's reading level is going to be way up here. So notice that as I went up on shoe size, I also went greater on reading level. Okay, so the higher I go on shoe size, the higher I go on reading level. And this is something about a correlation. It is a correlation. It represents a relationship between the two variables, whereas one of the variables increases, the other also increases. So when you see one, you're more likely to see the other. Examples would be height and weight. Taller people, on average, tend to weigh more, especially if you think of like children versus adults. The taller you are, usually the more you weigh. I'm an exception. But anyway, so those are positive correlations, okay? The more education you have, the more money you're likely to make. The more clouds you see outside, the more likely it is to rain. So this is a kind of correlation that's called a positive correlation. So there's two things that we're going to learn about correlations, the direction and the strength. And the first thing we're going to learn is the direction of a correlation. And in a positive direction, or in other words, a positive correlation, what this means is that first we denote it with a positive sign. And what it means is if one of the variables goes up, the other goes up, or if the first goes down, the second go down. So basically, the variables here are going to move, move in the same direction. Okay, so that's the direction of a correlation. Now there's another direction, and that's called negative. And a negative correlation, also called a, coming to me, sorry. A negative correlation, or a, doggone it, on the tip of my tongue. Anyway, inverse correlation. Inverse is another word, sorry. All right, so a negative correlation is denoted with the negative sign. And it means that as one of those variables goes up, the other goes down. Or if the first one goes down, the second one goes up. So the variables here are not going to move in the same direction, but they move in the opposite direction. Okay? Negative correlation versus positive correlation. Variables move in the same direction in a positive. In a negative, they move in opposite directions. Okay, so let's talk about a correlation that we might do where we take a bunch of neighborhoods in a city. And so we're taking a lot of neighborhoods, and like I said, we probably want to do at least 100. Correlations are typically done on pretty large groups, and it can be in more than one city. And here we can have the poverty rate. So I'm going to look at the poverty rate in those neighborhoods, and then I'm going to look at the crime rate. So when I plot it, here's what I'm going to notice. Here's the poverty level, and here's the crime rate. Now, low poverty means you got the bling bling, okay? Cha-ching, cha-ching. Low poverty is a lot of money. High poverty, you ain't got much, okay? Crime rate, low means there's not a lot of crime. High, lots of crime. So when I get these measures for each of these neighborhoods and I start plotting them, I might notice something like this. I might notice this tendency for the neighborhoods to go in this direction. If you recognize that, that's a positive correlation. Because when we do a positive correlation, not only do the variables move in the same direction, but when we plot it, it goes like this. Okay? So we have this positive correlation telling us that in low poverty areas, we tend to have low crime rates. So this is on the low end and this is on the low end. But as we go up, okay, then when we have high poverty rates, we tend to have higher crime rates. So that's a positive correlation. Now let's see how else we could do this. Instead of looking at poverty rate, I could just look at income here. If I'm comparing income to the crime rate, then when I go to make that graph, here's income, not poverty, but income, and here's crime rate. So low income means you have no money, and high income means you got the plenty, okay? So here's low crime rate and high crime rate. So here's what happens. When you plot those same neighborhoods, if you're looking at income and not poverty, they're going to look like this. As you might guess, this is a negative correlation. So this is a negative correlation because as income increases, crime rate goes down. So they move in opposite directions. So one of the things about that negative correlation that I told you about, not only does it go like this and do they move in opposite directions, and we denote it with this negative sign, but also when you plot it, it goes like this. It's a descending trend rather than an ascending trend. Okay, so that's a negative correlation. So that is the direction of a correlation. You got positive, you got negative. The positive means that the two variables move in the same direction. As one goes up, the other goes up. Negative means one goes up, the other goes down. So in a positive, you see one thing, you're more likely to see this other thing. When two things are inversely related, it means that as one of those things, as you see that, you're less likely to see this other. So the next thing we want to talk about is the strength of a correlation. The strength of a correlation tells us how closely related the two variables are. And it has everything to do with prediction, because we want to know how well can we predict one thing from the other. If I know one variable, how well can I predict another? So when we talk about strength, we talk about different kinds. For example, there's a perfect correlation, and then there's a non-perfect correlation. A perfect correlation means that I'm going to predict perfectly. If I have one number on one axis here, on the other axis I have an exact number. So I can go from one exact number to another exact number. A non-perfect correlation means that I have to go from one number to not in line, but to a range of scores from here to here, okay? Sorry, I messed that up really good. Let me show you that again. Okay, so if I have a non-perfect correlation, then maybe my correlational plots are like that, and I go here, I can predict from this number to a range of numbers over here, this range, okay? Not to an exact number, not from an exact number to an exact number, but from an exact number to a range. All right, so let's talk about that. First, let's pretend we're in a perfect world where you might actually get a perfect correlation. So let's say that I was looking at your high school SAT score, the Scholastic Aptitude Test that you took before college, while you were in high school, to see which college would let you in. And here, I'm going to look, the second variable I'm going to look at is your first year college GPA. Okay, so what is your grade point average after 30 hours of college? Now, I'm going to make my life easy. Let's go with 1, 2, 3, 4. 1, 2, 3, 4. Okay? Back when I was in school, the SAT would only go up to 1,600. Now I think it's back to that, but it used to be some 20 something. All right, so 400, 800, 1,200, 1,600, and GPA back in my day was 1.0, 2.0, 3.0, and 4.0. You couldn't get anything over a 4.0. So let's say I take 100 people. Now notice these people don't even know they're in a study, right? All I have to do is take 100 people from a school system, some college, and look at what was their high school GPA and now what was their GPA at the end of college. So let's say this person made an SAT of 800 and they made a 2.0. And this person made a 1,200 and they made a 3.0. And this person made 1,000 and they made a 2.5. And this person made a 1,400 and they made a 3.5. And this person made an 800 and they made a 2.0. And then we got person number 6 and 7 all the way to 100, okay? So let's say we got number here, it's another person who scored 1,000 and they scored a 2.5 and so forth. When I go to plot these, 802, 1,203, 1,000 and 2.5, 1,400 and 3.5, 802 again, okay? 1,000 and 2.5 again. Let's say I plot all 100 and they come out on a straight line like this. That would be a perfect correlation. Why? Because look how I can predict. If you tell me I made an 800 on my SAT score, what's my GPA going to be? I can tell you 100% of the time, people who make an 800 score a 2.0. This doesn't happen in real life. Not at all, okay? So this doesn't happen in psychology, sociology, economics, all of the sciences that aren't exact, and it doesn't happen sometimes in the exact sciences either. But notice that in a perfect correlation, I predict perfectly. If you told me I made a 3.0 in college, I would be able to say, hey, you know what? I bet I know that you made a 1200 on your SAT. And everybody that scores a 3 makes a 1200. And everybody who scores an 800 makes a 2.0. So of course this doesn't happen, but notice that it's perfect prediction. When I know one of your scores on this axis, I can predict it on the other. So when I know this variable, I can perfectly predict that variable. So, okay, that doesn't happen. Let's let me clear up some of these pages here. Okay, so let's talk about something about how it might go. All right. So let's do a few and let's talk about what might happen. So what I'm going to do now is I'm going to plot some plots, assuming that my numbers here were not like this, but were like I'm going to plot them, okay? So what I'm doing here is I'm saying, okay, 1, 2, 3, 4, 1, 2, 3, 4 for each of these. All right, so once again, we have SATs here, okay? That's your SAT. And down here we have GPA. So your GPA is either a 1, 2, 3, or 4, and your SAT is either a 400, 800, 1200, or 1600. Okay, so I'm going to put this in a little bit less obvious. So 1, 2, 3, 4, 400, 800, 1200, 1600. Okay, so all of them will be the same. 400, 800, 1200, 1600, 400, 800, 1200, 1600, and our GPAs are 1, 2, 3, or 4.0. Okay? So what I'm going to do now is I'm going to ask you, what if when you took these scores and when you got each person's SAT score and their college GPA, and you looked at all of those, what if some of them landed right where a perfect line would be? So some of your people in your study landed right there. Some people made an 800 and they made a 2.0 and so forth. But other people didn't. Other people landed right outside the line, just outside the line. So now I'm not going to be able to predict based on a perfect score. I'm going to have to predict based on a range. So now what I'm going to do is I'm going to make a circle around my scores. And I'm going to go far enough out from the middle that I include 95% of my people. I can use 97 or 98 or 95. Usually we pick 95. 92 is another option. Okay? So 1, 2, 3, 4. Out of 100, I have 5 people that are not within the circle. So here's what I'm going to do now. Now I'm going to say, if you scored an 800 on the SAT, then your GPA is likely to fall between here, which is a 1.5, and here, which looks like a 2.25. So 1.5, 2.25, okay? So in other words, what I'm showing you here, 2.25, is that I can predict from an exact score to within a range of scores, okay? This is a non-perfect correlation because I'm predicting from one number to a range, this range here. All right, so let's say that you had a group of scores again. So you did the study and you have your people who scored these SAT scores, and when you plotted their GPA, it looked like this. Some people fell on the line. Some people fell right outside the line. And some people fell even further outside of the line. Okay? So now, I have to make my circle big enough to include 95% of my people. And now, so once again, 95% of the time, now I'm predicting you tell me, hey, I made an 800 on my SAT. What's my GPA going to be? I'm going to guess that it's between here, between a 1 and a 2.5. So look what happened. We went from 1.5 to 2.25 range to 1 to 2.5 range. So our range went up, or got larger, I should say. What if you plotted these scores that you got, and some landed on the line, some right outside the line, some a little further out, some a little further out. So now, to include 95%, you have to go out that far. You still got 5 of these out here of the 100. But notice now that when you tell me I made an 800, what's my GPA going to be? I'm going to predict that it's anywhere from here, let's call that a 0.25, all the way to here, which we'll call a 3.1, okay? To a 0.1 there, okay. So basically, this is getting to a range that it's very unhelpful. This wasn't very helpful either. This is a little more helpful. In other words, if I know you're going to score between a 1.5 and a 2.25, then I know you're probably not going to make the dean's list, okay? And you're not going to do as well. I probably don't want to let you in. Here, we got a broader range, so it's even less helpful. Now, this range is so broad that you may be on the dean's list all the way to failing. So when something is not correlated at all, the plot looks like this. When you go to plot them, the scores are all over the place. So it doesn't matter what you made on here. If you make an 800 here, you're just as likely to make a 0 as you are to make a 4. And if you made a 1600, you're just as likely to make a 0 as you are to make a 4. So this particular one shows no correlation whatsoever. These two things are not correlated. No correlation whatsoever is almost as hard to get as this perfect correlation. These just don't happen, and these basically don't either. Most things are correlated, even if one thing has nothing to do with the other, they're correlated a little bit. So this is a strong correlation because I can predict within a useful range. And this is a very weak correlation because they're related, but they're not where I can actually predict one thing from the other. And this is kind of a moderate correlation. So the moderate correlation lets me predict a little bit, but not much. So let's do this over again. Wow, I got a lot of crap there. Okay, so when we're looking at correlation, you have correlations that are where when you plot them, they look perfect. You have correlations that look like a little bit, here's where perfect would be, and they're just a little bit out off of that. And then sometimes when you look at the relationship between two things, you find that the relationship is a little further stretched. And other times you look and they're not very related at all. Here's where perfect would be, and they're all over the place, kind of here. So it's not very related at all. And then sometimes it tells you there's no relationship between these two things at all. It doesn't matter what you score on one or what you see on one variable. It doesn't impact the way that you see the other. Now, all of these happen to be positive correlations because they go in this direction. As one of these things increases, so does the other. As we go up on this, we go up on that, on X or Y, if you want to call it that. So these are all positive correlations. This we call a perfect correlation because we can predict from one exact number to another exact number. These are all non-perfect correlations because here we can predict from one number, X, to a range of Y. A range, okay? So this is a non-perfect correlation. This one, this one, this one. And this is no correlation at all. Now, the next thing we're going to talk about is what's called the Pearson R. The Pearson R is a little r. It's a, so Pearson little r like that. It's a correlation coefficient. A coefficient is another word for number. And Pearson R is a number that explains a correlation to us. It does that in two ways. It's going to have a number, which represents the strength of the correlation. And then it's going to have a sign, in other words, positive or negative. And this tells us the direction of the correlation. So these two things are completely separate from each other. The number has nothing to do with the direction or the sign. The strength has nothing to do with direction, sign, and the number are completely separate. So in other words, a perfect correlation that goes in this direction, which is positive, is just as strong as a negative correlation that goes in that direction. Because I can still predict from one exact number, x, to another exact number, y. From one exact number, x, to another exact number, y. So it doesn't matter if they're positive or negative correlations. What I'm doing is I'm perfectly predicting, so this is a perfectly strong, perfect correlation. Positive and negative, the direction has nothing to do with the strength. Okay, so Pearson R is a formula. And what you're going to do is you're going to put all your numbers into a formula, and it's going to come out. Pearson R will be equaling something, a number within a range from negative 1.0 all the way to positive 1.0. So this will be the range that Pearson R comes into. So in other words, when you take all these numbers that you got from things that you measured from your subjects, and you put them in the Pearson R formula, it's going to give you a little plot so you can physically see the correlation, and then it's going to give you a number. The number is going to be somewhere between negative 1.0 or positive 1.0, but it could also include these 1.0s. So positive 1.0 means that it's a perfect positive correlation. And negative 1.0 means that it's a perfect negative correlation. Then if Pearson were equal to 0, this would mean there's no correlation whatsoever. So then you have numbers like 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, and so forth. And these 0.7 all the way here are considered to be strong correlations, both on the positive or the negative side. So negative 0.90, negative 0.80, negative 0.70 are all considered to be strong. In other words, they represent a correlation where I can predict pretty closely. So this is a strong correlation. So this is moderate. A moderate correlation might be around here, the 0.6s. Okay? So this would be kind of moderate, not very good. And everything from negative 0.50 to positive 0.50, everything in between here, so negative 0.40 and etc., these were our very weak correlations. So what that means is that these strong correlations mean the two things are related, and they're related strongly. They're related in this direction in such a way that when one of these things goes up, the other goes up. And the perfect negative correlation or the strong negative correlations tell us these two things are related closely. And we can closely predict one thing from the other, but the way we predict is that as one of these goes up, the other goes down. On the other hand, these moderate correlations don't really allow us very good prediction. And these weak correlations means these things are related, but they're not related very well. So we really are not going to have much luck predicting one from the other. Of course, no correlation whatsoever right in the middle here means you can't predict them at all. So Let's make sure you get that. Okay, so you have Pearson R, which is the correlation coefficient. Basically the number that tells us what a correlation means. When a plot looks like perfectly negative or perfectly positive, this is positive 1.0, negative 1.0. So the Pearson R is negative 1.0 when it perfectly goes this way, and positive 1.0 when it perfectly goes that direction. When there's a 0, it means there's no correlation. If you plot that, it looks like a big square or circle, okay? And then something like a 0.80 would be a plot that here's where perfect would be, and it sticks pretty close to perfect. So when you predict within a small range, okay? So you predict from here to this range here. Negative 0.80 means the same thing, but in the other direction. So here's where positive would be, and you have a little range so that you can predict from here to there. So once again, you're predicting within a small range from here to this range here. And these are equally strong. This one and this one are equally strong, just like 1 and 1 are equally strong. And negative 0.30 and positive 0.30 are equally weak, okay? So, let's look at these numbers. I guess I should leave it like that. Okay, so let's look at these numbers. R equals 1.0, R equals negative 1.0. Which one of these is stronger? Trick question. These are equally strong, okay? These are the strongest you can get. So what's stronger? Positive 0.30, negative 0.90. The stronger correlation, not looking at these, this is the stronger correlation. When you're looking at the strength, you look at the absolute number. In other words, you ignore that sign. This is all you look at when you're looking at strength, the 0.30 and the 0.90. The closer it is to 1, the stronger, okay? So, in other words, the more closely related those two things are. So, once again, positive 0.70, negative 0.40. This is the stronger correlation. We ignore the sign. The closer it is to 1, the closer those two things are related, which means the closer we can, or the better we can predict one from the other. Hope that helped. Thank you.